Mercury is the closest planet to the Sun. It sits right next door compared to the frozen worlds at the edge of our solar system. So reaching it should be simple, fast, easy. It is none of those things. The European Space Agency confirmed that sending a spacecraft into orbit around Mercury requires more energy than sending one all the way to Pluto. BepiColombo launched in 2018 and will not arrive until late 2026, after 9 gravity assist flybys and 8 years of braking against the Sun's pull. Meanwhile, a flyby of distant Neptune took Voyager 2 just 12 years. The solar system is not a highway. It is a gravitational maze where closer does not mean faster, and the shortest distance is almost never the quickest path. If you enjoy journeys that completely reshape how you think about space and time, do us a huge favour and hit that like button. And if you have not already, subscribe to the channel. It genuinely helps us keep making these deep dives. Now, settle in and get yourself comfortable. Let's begin. Ask someone how long it takes to reach another planet, and they will almost certainly do the same thing. They will look up the distance, divide it by the speed of a spacecraft, and give you a number. Mercury is close, so it should be fast. Neptune is far, so it should take a while. It sounds perfectly logical. It is also completely wrong. This mistake is not just common, it is nearly universal. Every classroom diagram reinforces it. Posters show the planets lined up in a neat row, equally spaced, sitting still, waiting to be visited like cities on a highway. Documentaries zoom the camera outward from the Sun and glide past each world in order, as though a spacecraft could simply follow the same path. Even experienced science communicators fall into the trap of presenting the solar system as a map of fixed destinations. But the solar system is not a map. The planets are not sitting still, and spacecraft do not travel in straight lines. The moment you understand why, everything about interplanetary travel changes. The neat mental picture dissolves. What replaces it is stranger, more beautiful, and far more frustrating than anything the simple model suggests. Because the real solar system is a machine, a colossal gravitational clockwork where every world is in constant motion, every trajectory is a curve, and the fastest route to a destination is almost never the most obvious one. To understand how missions actually work, you have to start with an uncomfortable truth about motion in space. When a rocket launches from Earth, it does not start from rest. Earth is already moving. Our planet orbits the Sun at roughly 67,000 miles per hour. That velocity is baked into the spacecraft the instant it leaves the launch pad. The rocket does not need to generate all of its speed from scratch. It inherits Earth's orbital velocity and then adds to it or subtracts from it depending on where it wants to go. This is the first crack in the simple model. A spacecraft heading to Mars does not simply aim at Mars and fire its engines. It enters an orbit around the Sun, a long curving ellipse that starts at Earth's distance from the Sun and stretches outward until it intersects Mars's orbit. The spacecraft coasts along this ellipse, unpowered for most of the journey, falling along a gravitational arc shaped entirely by the Sun's pull. This type of trajectory has a name. It is called a Hohmann transfer orbit, after the German engineer Walter Hohmann, who described it in 1925, and it remains the foundation of nearly every interplanetary mission ever flown. A Hohmann transfer to Mars takes approximately 259 days, not because Mars is a fixed distance away, but because the elliptical path connecting Earth's orbit to Mars's orbit has a specific size, and the time to travel halfway around that ellipse is determined by orbital mechanics, not by engine power. You cannot simply burn your engines harder and arrive sooner. You can use a faster trajectory, but it costs enormously more fuel. And fuel is mass, and mass is the single most precious and limited resource in spaceflight. Every extra kilogram of propellant means a larger rocket, a higher cost, and a narrower set of missions that can be accomplished. So most missions accept the Hohmann transfer and its built-in travel time. But here is where the real complication begins. A Hohmann transfer only works when Earth and the target planet are in the right positions relative to each other. The spacecraft leaves Earth at one point in its orbit and arrives at Mars when Mars happens to be at the far end of the transfer ellipse. If Mars is not there when the spacecraft arrives, the mission fails. There is no stopping in space to wait. There is no turning around. The spacecraft will sail past the empty point in Mars's orbit and continue on its own elliptical path around the Sun, accomplishing nothing. This constraint creates what engineers call a launch window. For Mars, the geometry aligns roughly every 26 months. Miss the window, and the next opportunity is more than 2 years away. Every Mars mission in history, from Mariner 4 in 1964 to Perseverance in 2020, launched during one of these narrow windows. The window is not a suggestion, it is a physical law. Think of it like arriving at an airport gate. The plane leaves at a specific time regardless of whether you are on board. Except in this case, the gate only opens once every 2 years. Different planets have different launch windows because they orbit the Sun at different speeds and distances. Venus windows open roughly every 19 months. Jupiter windows appear approximately every 13 months. The farther out the planet, the more slowly it moves, and the timing between favourable alignments shifts accordingly. Every mission is a negotiation between the spacecraft's energy, the planet's position, and the geometry of the Sun's gravitational field. None of it has anything to do with drawing a straight line between 2 points. Now consider Venus. It is Earth's closest planetary neighbour. At its nearest approach, Venus comes within about 25 million miles of Earth, far closer than Mars ever gets. A Hohmann transfer to Venus takes roughly 146 days, making it one of the shortest interplanetary trips possible. Historically, Venus has been the most visited planet by spacecraft. The Soviet Venera program sent a series of probes beginning in the 1960s. Magellan mapped the surface with radar in the early 1990s. The European Space Agency's Venus Express orbited the planet from 2006 through 2014. These missions reached Venus relatively quickly because the orbital mechanics are favourable. Falling inward toward the Sun from Earth's orbit to Venus's orbit requires less energy than climbing outward to Mars. The transfer ellipse is smaller, the travel time is shorter. Venus has been visited more than any other planet. Roughly 50 missions have targeted it since the early 1960s, counting flybys, orbiters, landers, and atmospheric probes. The Soviet Union's Venera program alone sent more than a dozen spacecraft, and several of them accomplished something that remains one of the most audacious achievements in the history of planetary exploration. They landed on the surface and survived long enough to send back data. Surviving on Venus is an entirely different challenge from reaching it. The planet's surface temperature hovers around 870 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface is roughly 90 times what you experience standing at sea level on Earth. That is equivalent to the pressure roughly half a mile beneath the ocean's surface. And the atmosphere itself is almost entirely carbon dioxide, laced with clouds of sulfuric acid that would dissolve most metals. Venera 7, which landed in December 1970, became the first spacecraft to transmit data from the surface of another planet. It survived for approximately 23 minutes before the heat destroyed its electronics. Venera 9, arriving in October 1975, sent back the first photographs ever taken from the surface of another world. The images showed a landscape of flat, fractured rocks under a dim orange sky. Venera 13, which landed in March 1982, survived for 127 minutes, the longest any spacecraft has ever endured on Venus's surface. It transmitted colour photographs and even recorded the sound of Venusian wind, the first audio ever captured on another planet. These missions illustrate a principle that applies to every planet in the solar system. Reaching a world is only half the problem. What a spacecraft must endure when it arrives defines the true difficulty of the mission. Venus is easy to reach but brutal to survive. Mars is moderately difficult to reach but relatively gentle once you arrive. Mercury is agonizingly difficult to reach, but its surface, while extreme in temperature, is at least a vacuum without crushing atmospheric pressure. Each planet presents a unique combination of transit challenge and destination challenge, and no simple ranking captures the full picture. The upcoming decade promises a return to Venus after a long hiatus. NASA's Da Vinci mission, along with the European Space Agency's Envision, are planned for launch in the late 2020s or early 2030s. A companion NASA mission called Veritas was also selected, but has been placed on indefinite hold due to budget constraints. Leaving its future uncertain, Da Vinci will send an atmospheric probe plunging through Venus's thick atmosphere, measuring its composition during a roughly 63-minute descent. These missions will reach Venus in months. The question is not whether we can get there, it is whether our instruments can survive long enough to answer the questions we have been asking since the Venera landers sent back their final, heat-warped transmissions more than 40 years ago. But reaching Venus quickly does not mean reaching Venus easily. A spacecraft approaching Venus is falling deeper into the Sun's gravity well. It picks up speed as it drops inward. If the mission is a flyby, this extra speed is acceptable. The spacecraft screams past Venus and continues on its way. But if the mission needs to enter orbit, the spacecraft must slow down enough to be captured by Venus's gravity. That requires burning fuel to shed the excess velocity gained from falling sunward. Venus does have one advantage here. Its thick atmosphere can be used for aerobraking, where a spacecraft skims through the upper atmosphere to gradually reduce its speed. But this technique carries risk and adds complexity. The fundamental point remains. Even Venus, the closest and seemingly simplest target, demands careful trajectory planning and precise timing. Mars is the planet humans know best. We have sent more missions to Mars than to any other world. Rovers have crawled across its surface. Orbiters have mapped it in extraordinary detail. Landers have listened to Martian wind. And every single one of those missions was governed by the same orbital mechanics that govern all spaceflight. The travel time to Mars varies significantly depending on the specific launch window and trajectory chosen. Mariner 4, the first successful Mars flyby, launched in November 1964 and reached Mars in July 1965 after a journey of 228 days. Mariner 7, launched in 1969, made the trip in just 128 days on a faster trajectory. Viking 2, which launched in 1975, took 360 days because its trajectory was designed to deliver a heavy lander to the surface rather than simply fly past. Perseverance, launched in July 2020, arrived at Mars in February 2021 after 204 days. These numbers are not random. They reflect the specific geometry of each launch window, the mass of each spacecraft, and the mission objectives. A heavier spacecraft requires more fuel to accelerate, which often means a slower, more fuel-efficient trajectory. A flyby can take a faster path because it does not need to slow down. A lander needs extra precision in its approach, which constrains the trajectory further. The range of Mars travel times, from roughly 4 months to nearly a year, illustrates a principle that applies to every planet. There is no single answer to the question of how long it takes. The answer depends on when you launch, what you are flying, and what you intend to do when you arrive. The reason Mars travel times vary so dramatically deserves closer examination, because it reveals something essential about how the solar system works. Mars does not orbit the Sun in a perfect circle. Its orbit is noticeably elliptical, more elongated than Earth's. This means the distance between Earth and Mars at closest approach changes significantly from one opposition to the next. An opposition is the moment when Earth passes directly between Mars and the Sun, placing the two planets on the same side of the solar system. Oppositions occur roughly every 26 months, but not all oppositions are equal. During a favourable opposition, Mars can come within about 35 million miles of Earth. During an unfavourable opposition, the gap widens to roughly 63 million miles. That is nearly double the distance. A mission launching during a favourable opposition benefits from a shorter transfer arc and a faster arrival. A mission launching during an unfavourable opposition faces a longer path and a slower cruise. The difference can be months. Mariner 7, launched during the exceptionally favourable 1969 window, reached Mars in just 128 days. Viking 2, launched during a less favourable window in 1975, took 360 days. Both missions were expertly designed. The difference was not the spacecraft, it was the geometry of the solar system at the moment of launch. This variability has practical consequences for mission planning that most people never consider. A rover mission requires more than just reaching Mars. The spacecraft must arrive at a precise angle and velocity to enter the atmosphere correctly, deploy its heat shield, fire its parachute, and execute a powered landing sequence that places it within a few miles of the intended target. The Perseverance rover launched on July 30th, 2020, during a 3-week launch window. If the mission had missed that window, the next opportunity would not have arrived until late 2022. 2.5 years of delay because of planetary geometry. The spacecraft was ready, the rocket was ready, the science team was ready. None of that mattered. The solar system sets the schedule, and no amount of human readiness can override orbital mechanics. The entry, descent, and landing sequence at Mars adds another dimension to mission difficulty. Mars has an atmosphere, but it is thin, less than 1% the density of Earth's at sea level. That is enough to generate dangerous heating during entry, but not enough to slow a heavy spacecraft sufficiently with a parachute alone. Every Mars lander since the Vikings has required some combination of heat shields, parachutes, retro rockets, and in the case of Curiosity and Perseverance, a sky crane that lowered the rover on cables from a hovering descent stage. This entire sequence unfolds during roughly 7 minutes of communication blackout, when the spacecraft is on its own, executing pre-programmed commands with no possibility of real-time control from Earth. Engineers at the Jet Propulsion Laboratory call this interval the 7 minutes of terror. The spacecraft has travelled for 7 months across hundreds of millions of miles, and its entire mission comes down to a fully automated landing sequence lasting less time than a coffee break. And then there is Mercury. If the solar system were a highway, Mercury would be the exit closest to the on-ramp. It orbits the Sun at an average distance of only about 36 million miles. Mars, by comparison, orbits at roughly 142 million miles. Intuition says Mercury should be far easier and faster to reach than Mars. Intuition is spectacularly wrong. Mercury is one of the hardest planets in the entire solar system to visit. The European Space Agency has stated plainly that placing a spacecraft into orbit around Mercury requires more energy than sending one to Pluto. That sentence deserves a moment to sink in. Pluto sits roughly 40 times farther from the Sun than Earth does. Mercury sits less than half Earth's distance from the Sun, and yet getting to Mercury and staying there is the harder problem. The reason is the Sun. Everything in the inner solar system is dominated by the Sun's gravity. Earth orbits the Sun at approximately 67,000 miles per hour. To reach Mercury, a spacecraft must fall inward, closer to the Sun, but falling inward means speeding up. The Sun's gravity accelerates everything that drops toward it, just as a ball rolling downhill gains speed. By the time a spacecraft reaches Mercury's orbital distance, it is moving far too fast to be captured by Mercury's weak gravity. Mercury is small. Its mass is only about 5.5% of Earth's. Its gravitational pull is feeble compared to the speed of an incoming spacecraft. A flyby is manageable. Mariner 10, launched in November 1973, reached Mercury in March 1974 after just 147 days. It flew past the planet 3 times between 1974 and 1975, becoming the first spacecraft to visit Mercury. But Mariner 10 never entered orbit. It simply sailed past, snapping photographs during brief encounters before continuing on its own orbit around the Sun. Entering orbit around Mercury is an entirely different challenge. The spacecraft must arrive slowly enough relative to Mercury that the planet's gravity can capture it. But arriving slowly near the Sun is extraordinarily difficult because the Sun's gravity is constantly pulling the spacecraft faster. The solution is not raw engine power, it is patience. NASA's Messenger mission demonstrated this. Messenger launched in August 2004 with the goal of orbiting Mercury. It did not arrive in orbit until March 2011. The journey took 6.5 years. During that time, Messenger performed 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself. Each flyby was a gravity assist, a carefully calculated maneuver where the spacecraft passed close to a planet and used that planet's gravity to adjust its speed and trajectory. The flybys gradually bled away Messenger's excess velocity, lowering its orbit closer and closer to Mercury's path around the Sun. Only after years of this gravitational braking was Messenger moving slowly enough to fire its engines and slip into Mercury orbit. BepiColombo, the joint European-Japanese mission launched in October 2018, takes this process even further. BepiColombo is scheduled to enter Mercury orbit in November 2026, roughly 8 years after launch. Its trajectory includes 9 gravity assist flybys, 1 of Earth, 2 of Venus, 6 of Mercury. Each flyby tightens the spacecraft's orbit, shaving away speed that cannot be removed any other way. BepiColombo also carries ion thrusters that fire continuously during the cruise phase, providing a gentle but sustained braking force against the sun's relentless gravitational pull. Even with this advanced propulsion, the journey takes the better part of a decade. Compare this to reaching distant worlds. New Horizons, launched in January 2006, passed Jupiter just 13 months later. It reached Pluto in 9.5 years. Voyager 2 reached Jupiter in about 2 years. These outer planet missions are heading away from the Sun, climbing uphill out of the Sun's gravity well. They need to gain energy, and gravity assists from Jupiter provide exactly that. The physics works in their favor. Mercury missions fight the opposite battle. They must lose energy, shed speed, and decelerate against the strongest gravitational force in the solar system. The Sun does not help spacecraft reach Mercury. The Sun is the obstacle. This counterintuitive reality reveals something fundamental about how the solar system works. Distance from Earth is a poor predictor of mission difficulty or travel time. What matters is the energy budget. How much speed must a spacecraft gain or lose to match the orbit of its target? For outer planets, the spacecraft needs to gain energy to climb away from the Sun. Gravity assists from massive planets like Jupiter provide free energy along the way. For Mercury, the spacecraft must dump enormous amounts of energy to fall inward and slow down. There are no convenient massive planets between Earth and Mercury to provide braking assists. Venus helps somewhat, and Mercury itself can be used for repeated flybys, but the process is slow, complex, and demands extraordinary precision in navigation. The concept that captures this is called delta V. It represents the total change in velocity a spacecraft must achieve to complete its mission. Delta V is the true currency of spaceflight. It determines how much fuel is needed, how large the rocket must be, and how long the journey will take. A mission with a high delta V requirement is expensive and difficult regardless of the physical distance involved. Mercury has one of the highest delta V requirements of any planet in the solar system, which is why it has been visited by only 3 missions in the entire history of spaceflight. Mars, despite being farther away, has been visited by more than 50. To understand how dramatically delta V reshapes our intuitions about the solar system, consider some specific numbers. A Hohmann transfer from Earth to Venus requires a delta V of roughly 3.5 kilometers per second. A similar transfer to Mars requires approximately 3.6 kilometers per second. These figures are comparable, which is why both planets are relatively accessible and have been visited many times. Now consider the outer planets. A Hohmann transfer to Jupiter requires approximately 6.3 kilometers per second of delta V. Saturn demands roughly 7.5. These are higher but still achievable with existing launch vehicles and gravity assists. The numbers climb steeply, but the missions are feasible because the spacecraft is gaining energy, climbing outward from the Sun, and gravity assists provide much of the needed velocity for free. Mercury breaks the pattern entirely. Entering orbit around Mercury demands a total delta V that is among the highest in the solar system, roughly comparable to what is needed to reach Jupiter orbit. But there is a critical difference. Jupiter-bound spacecraft gain energy from gravity, assists at massive planets. Mercury-bound spacecraft must lose energy, and there are no massive planets between Earth and Mercury to provide efficient braking. Venus is the only available assist, and it is far less massive than Jupiter. This forces missions like BepiColombo to perform multiple flybys over many years, using each encounter to shed a small amount of velocity. The process is effective, but agonizingly slow. Return to the fact introduced at the beginning of this story. Mercury orbit insertion demands more energy than a mission to Pluto, despite Pluto sitting roughly 40 times farther from the Sun than Earth does. The numbers confirm it. Mercury sits less than half of Earth's distance from the Sun, and yet the energy budget to get there and stay is larger. That is not a curiosity. It is a demolition of the idea that distance determines difficulty in space travel. Energy is the real currency. Distance is merely a side effect of the orbits that energy buys. This also explains why the question in this episode's title is so much harder to answer than it first appears. If someone asks how long it takes to fly from New York to Los Angeles, the answer is roughly 5 hours. The distance is fixed, the route is known, the speed is predictable. But if someone asks how long it takes to reach Mars, the honest answer is that it depends on at least half a dozen variables. When did you launch? What trajectory did you use? Are you flying past or entering orbit? 8. How heavy is your spacecraft? Did you use gravity assists? Each variable shifts the travel time by weeks or months, and Mars is the easy case. For Mercury, the variables shift the travel time by years. The inner solar system teaches a brutal lesson. Venus is reachable in months. Mars is reachable in months. But Mercury, the planet closest to the Sun, can take the better part of a decade to orbit. The simple ranking of planets by distance from Earth tells you almost nothing about how long a mission will take or how hard it will be. What matters is not where a planet is, but how it moves, how fast it orbits, how deep it sits in the Sun's gravitational well, and whether a spacecraft needs to merely pass by or actually stop. And this is only the inner solar system. 3 rocky worlds within a couple of 100 million miles of Earth. The journey outward, past the asteroid belt, into the realm of gas giants and ice giants, introduces challenges that make the inner planet difficulties look modest by comparison. Because out there, the distances are not measured in millions of miles. They are measured in billions. The travel times are not measured in months. They are measured in years. And the difference between flying past a giant planet and entering its orbit can be the difference between a mission that takes 2 years and one that takes more than a decade. The solar system is only beginning to reveal its true scale, and every step outward makes the rules of the game more demanding, more counterintuitive, and more humbling. The next step takes us past the asteroid belt, where Jupiter waits like a gravitational gatekeeper, and where the single most important trick in all of spaceflight turns an impossible journey into merely an improbable one. Beyond the asteroid belt, the solar system changes character. The rocky inner worlds give way to something vastly larger, vastly more distant, and vastly more demanding. Jupiter orbits the Sun at an average distance of roughly 484 million miles. Saturn sits nearly twice as far out, at approximately 886 million miles. These are not modest steps outward. They represent a leap into a different scale of spaceflight entirely. And reaching them introduces a problem that would have been impossible to solve with brute force alone. The problem is energy. A spacecraft leaving Earth has only so much fuel. Chemical rockets burn their propellant in minutes during launch, accelerating the spacecraft to the velocity needed to escape Earth's gravity. After that, the spacecraft is coasting. It has no more fuel for dramatic speed changes. It drifts along its orbital path around the Sun, shaped by gravity alone, carrying whatever velocity it had when the engines shut down. For a mission to Jupiter using a simple Hohmann transfer, the coast would take roughly 2 years and 9 months. For Saturn, it would stretch to more than 6 years, and those are the minimum energy trajectories. They assume the spacecraft carries just enough fuel to enter the transfer orbit and nothing more. But minimum energy trajectories create their own problems. They deliver the spacecraft to the target planet at relatively low speed, which is fine for a flyby. The spacecraft sails past, collects data for a few hours or days, and continues on its way. If the goal is to enter orbit, however, the spacecraft must slow down significantly upon arrival. At Jupiter, the planet's enormous gravity accelerates incoming spacecraft to tremendous velocities. A probe arriving on a Hohmann transfer would be moving so fast relative to Jupiter that it would need to burn a huge amount of fuel to slow down enough for orbital capture. Fuel it probably does not have. The mass penalty of carrying that extra propellant would have required a much larger rocket at launch, and in many cases, such a rocket simply did not exist or could not be afforded. This is where the most elegant trick in all of spaceflight enters the story. It is called the gravity assist, and it changed everything. The concept was first demonstrated practically by the Italian mathematician BepiColombo, who in the early 1970s proposed using a Venus flyby to alter the trajectory of NASA's Mariner 10 spacecraft on its way to Mercury. The idea is deceptively simple. A spacecraft flies close to a planet, and the planet's gravity bends the spacecraft's path and changes its speed relative to the Sun. From the planet's perspective, the spacecraft swings around and leaves at the same speed it arrived. No energy is created or destroyed in the planet's frame of reference. But from the Sun's perspective, The spacecraft has gained or lost significant velocity because it borrowed momentum from the planet's own orbital motion. Think of it like a game of cosmic billiards. The planet is a moving ball with enormous mass. The spacecraft is a tiny ball that bounces off the planet's gravitational field. If the spacecraft approaches the planet from behind, moving in the same direction as the planet's orbit, it picks up speed. The planet loses an infinitesimally tiny amount of orbital energy, so small it is unmeasurable, while the spacecraft gains a significant boost. If the spacecraft approaches from the front, opposing the planet's motion, it loses speed. The exchange is governed by conservation of momentum, one of the most fundamental principles in physics. And because planets are incomprehensibly more massive than any spacecraft, they can give away velocity without any detectable effect on their own orbits. To truly grasp how a gravity assist works, it helps to walk through one in slow motion using a real example. Consider Cassini's flyby of Jupiter in December of 2000. At that point in its journey, Cassini had already performed 2 Venus flybys and 1 Earth flyby over the previous 3 years. It was heading outward from the Sun, bound for Saturn, but it still did not have enough velocity to reach its destination on schedule. Jupiter provided the final boost. As Cassini approached Jupiter from behind, moving roughly in the same direction as Jupiter's orbit around the Sun, the planet's enormous gravitational field began pulling the spacecraft forward. Cassini accelerated, falling toward Jupiter along a curved path. The spacecraft did not aim directly at the planet. It was targeted to pass at a carefully calculated distance, close enough for a strong gravitational interaction but far enough to avoid the most intense radiation belts that surround Jupiter. At closest approach, Cassini swept past at roughly 6.2 million miles from Jupiter's cloud tops. During the approach phase, Jupiter's gravity accelerated Cassini significantly. At the point of closest approach, the spacecraft swung around the planet in a tight curve, its trajectory bending sharply. As Cassini departed on the far side, Jupiter's gravity now pulled backward on it, decelerating it. But here is the crucial subtlety. Because Cassini approached from behind Jupiter, the acceleration phase occurred while the spacecraft and the planet were moving in roughly the same direction. The deceleration phase occurred after the spacecraft's path had been bent, so it was now moving partly away from the planet's direction of travel. The net effect was a gain in velocity relative to the Sun of approximately 2 kilometers per second. That translates to roughly 4,500 miles per hour of free speed, achieved without burning a single drop of fuel. From Jupiter's perspective, the encounter was perfectly symmetric. Cassini arrived at a certain speed relative to Jupiter and left at the same speed relative to Jupiter. No energy was created, but from the Sun's perspective, the encounter was asymmetric. Cassini stole a tiny amount of Jupiter's orbital momentum. Jupiter, with a mass roughly 318 times that of Earth, lost an imperceptibly small fraction of its orbital velocity. The change to Jupiter's orbit was so small that it would take longer than the age of the universe to measure. But for Cassini, the change was transformative. That single flyby provided enough additional velocity to reshape its trajectory and deliver it to Saturn 2 years faster than a non-assisted path would have allowed. This is why the specific geometry of a gravity assist matters enormously. The angle of approach, the distance of closest flyby, and the relative motion of the spacecraft and the planet all determine how much velocity is gained or lost and in what direction the spacecraft departs. Mission designers spend years optimizing these parameters, running thousands of trajectory simulations to find the exact flyby geometry that delivers the spacecraft to its next destination at the right time and speed. A difference of a few hundred miles in closest approach distance can change the departure angle by enough to miss the next planet entirely. The precision required is extraordinary. The payoff is a free velocity change that would otherwise cost tons of propellant the spacecraft could never carry. This technique transformed interplanetary exploration. Without gravity assists, most outer planet missions would have been either impossibly expensive or impossibly slow. With gravity assists, engineers could design trajectories that hopscotch from planet to planet, picking up free velocity at each stop, reaching destinations that would otherwise have required rockets far beyond anything humanity has built. Jupiter became the centerpiece of this strategy for the outer solar system. It is the largest planet, with more than twice the mass of all other planets combined. Its gravitational field is immense. A spacecraft passing close to Jupiter can gain or lose thousands of miles per hour in velocity, enough to reshape its entire trajectory through the solar system. Nearly every mission to the outer planets since the 1970s has used Jupiter as a gravity assist waypoint, making it the single most important crossroads in deep space exploration. Pioneer 10 was the first spacecraft to cross the asteroid belt and reach Jupiter. It launched on March 2nd, 1972, aboard an Atlas Centaur rocket. Roughly 21 months later, in December 1973, it made its closest approach to Jupiter, passing within about 81,000 miles of the planet's cloud tops. Pioneer 10 was a flyby mission. It carried no capability to enter orbit. It screamed past Jupiter at tremendous speed, collecting data on the planet's magnetic field, radiation belts, and atmosphere during a brief encounter window. The scientific return was revolutionary. Pioneer 10 confirmed that Jupiter's radiation environment was far more intense than predicted, that the planet radiated more heat than it received from the Sun, and that the Great Red Spot was an enormous anticyclonic storm. But the spacecraft was past Jupiter and gone within days. The encounter was a snapshot, not a sustained study. Pioneer 11 followed roughly a year later. Launched in April 1973, it reached Jupiter in December 1974 and was deliberately targeted to fly closer to the planet than its predecessor, passing within roughly 27,000 miles of the cloud tops. Pioneer 11's trajectory was designed with a secondary purpose. Jupiter's gravity flung the spacecraft upward and outward, redirecting it towards Saturn. Pioneer 11 reached Saturn in September 1979, becoming the first spacecraft to visit the ringed planet. The total journey from Earth to Saturn, with a Jupiter gravity assist, took roughly 6.5 years. Without that assist, a direct Hohmann transfer to Saturn would have taken over 6 years anyway, but Pioneer 11's trajectory also provided a Jupiter encounter along the way, doubling the scientific return for a single mission. The Voyager mission's elevated gravity assists into an art form. Voyager 1 launched on September 5, 1977, and reached Jupiter in March 1979, roughly 18 months after launch. It passed within about 217,000 miles of Jupiter's cloud tops, studying the planet, its rings, and its major moons in unprecedented detail. The images of Io's active volcanoes, the first ever observed beyond Earth, stunned the scientific world. Jupiter's gravity then redirected Voyager 1 towards Saturn, which it reached in November 1980, about 3 years after leaving Earth. Voyager 2 launched slightly earlier, on August 20th, 1977, but on a slower trajectory. It reached Jupiter in July 1979 and Saturn in August 1981. But Voyager 2's trajectory was special. It was designed to preserve the option of continuing beyond Saturn to Uranus and Neptune, taking advantage of a rare planetary alignment. That story is coming. For now, what matters is the principle. Both Voyager spacecraft used Jupiter's gravity to reach Saturn faster and with less fuel than any direct trajectory could have achieved. Jupiter did not just accelerate them, it bent their paths, redirecting them precisely towards Saturn's location years in the future. The navigation required to thread a spacecraft through Jupiter's gravitational field and emerge on exactly the right heading for Saturn, accounting for the positions of both planets years in advance, represents one of the most extraordinary achievements in applied mathematics. But every one of these missions, Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, shared a critical limitation. They were all flybys. They visited Jupiter and Saturn at tremendous speed, collected data during encounters lasting days or weeks, and then departed forever. They never stopped. They never orbited. They never had the chance to study these worlds over months and years the way a dedicated orbiter could. The flyby is the cheapest and fastest ticket to a distant planet, but it is also the shallowest. A flyby of Jupiter is like driving past a foreign city at 100 miles per hour with the window cracked open. You catch a glimpse. You learn something, but you do not truly understand the place. Entering orbit is an entirely different proposition, and it was Galileo that first demonstrated how much harder and slower that proposition is. Galileo launched on October 18th, 1989. Its destination was Jupiter, the same planet that Pioneer 10 had reached in 21 months. Galileo did not arrive at Jupiter until December 1995. The journey took 6 years and 2 months. Why did an orbiter need more than 3 times as long as a flyby to reach the same planet? Part of the answer lies in Galileo's tortured trajectory. Originally designed to be launched on a direct path to Jupiter, using a powerful Centaur upper stage carried inside the space shuttle, the mission was redesigned. After the Challenger disaster in 1986, led to a ban on carrying high-energy upper stages in the shuttle payload bay. Without the Centaur, Galileo lacked the raw power to reach Jupiter directly. Engineers had to find another way. The solution was gravity assists. Galileo flew past Venus once and Earth twice, using each flyby to gradually build up speed. This indirect route added years to the journey, but kept the mission alive. But the detour was only the beginning of Galileo's problems. The years of additional cruise time introduced a risk that shorter missions never face. Hardware degrades. Components that function perfectly at launch may fail after years of exposure to the radiation, thermal cycling, and micrometeorite bombardment of deep space. The longer a spacecraft travels, the more opportunities the universe has to break something critical. Galileo proved this in the worst possible way. In April 1991, roughly 18 months after launch, mission controllers commanded Galileo's high-gain antenna to unfurl. This umbrella-shaped dish, nearly 16 feet across, was the spacecraft's primary communication link. It was designed to transmit data back to Earth at 134 kilobits per second, fast enough to send detailed images and scientific measurements from Jupiter in near real time. The antenna did not open. Several of its 18 ribs remained stuck, likely because the lubricant on their joints had been damaged during the years Galileo spent in storage after the Challenger disaster delayed its launch. Engineers tried everything. They fired the deployment motor repeatedly. They rotated the spacecraft to heat and cool the antenna in alternating sunlight and shadow, hoping thermal expansion would free the stuck ribs. They pulsed the motor in rapid bursts to shake the mechanism loose. Nothing worked. The high-gain antenna never opened. This single mechanical failure threatened to destroy the entire mission. Without the high-gain antenna, Galileo was limited to its low-gain antenna, a small omnidirectional unit designed for basic telemetry during the early cruise phase. Its data rate was roughly 10 bits per second. That is not a typo. 10 bits per second. Compared to the 134,000 bits per second the high-gain antenna would have provided. At that rate, transmitting a single high-resolution image of Jupiter would have taken weeks. The science return would have been negligible. Billions of dollars and years of travel for a trickle of data barely distinguishable from silence. What happened next was one of the most remarkable rescue efforts in the history of space exploration. Over the remaining 4 years of Galileo's cruise to Jupiter, engineers at the Jet Propulsion Laboratory essentially rebuilt the mission from the ground up. They developed new data compression algorithms that could squeeze images and measurements into a fraction of their original file sizes. They reprogrammed the spacecraft's onboard computers, uploading new software across hundreds of millions of miles, teaching a machine built in the 1980s to process data in ways its designers had never anticipated. They upgraded the deep space network's receiving antennas on Earth, squeezing every possible bit of sensitivity from the ground segment. By the time Galileo reached Jupiter in December 1995, ground station upgrades had boosted the raw data rate to roughly 160 bits per second. A new onboard compression software multiplied the effective science return several times beyond that. The result was still less than 2% of the original design capability, but it was enough. Galileo returned transformative science from Jupiter over the next 8 years, discovering evidence of a subsurface ocean on Europa, observing volcanic eruptions on Io in unprecedented detail, and measuring Jupiter's atmosphere and magnetosphere. Galileo also carried an atmospheric probe that separated from the orbiter 5 months before arrival and plunged directly into Jupiter's atmosphere on December 7, 1995. The probe slammed into the upper atmosphere at over 100,000 miles per hour, decelerating so violently that it experienced forces of approximately 230 times Earth's gravity. A heat shield absorbed temperatures exceeding 28,000 degrees Fahrenheit. After slowing sufficiently, the The probe deployed a parachute and began transmitting data as it descended through Jupiter's cloud layers. It measured atmospheric composition, temperature, pressure, wind speed, and cloud structure. It survived for 58 minutes before the increasing pressure and temperature crushed and melted its instruments. Those 58 minutes remain the only direct in-situ measurements of any giant planet's atmosphere ever obtained. No other mission has attempted it since. Galileo's ordeal illustrates a truth about multi-year cruise phases that raw timelines cannot convey. Every additional year of travel is another year for something to fail. Shorter missions face lower cumulative risk. A spacecraft that reaches Mars in 7 months has 7 months' worth of exposure to the hazards of deep space. A spacecraft that takes 6 years to reach Jupiter has more than 10 times that exposure. Galileo survived its antenna failure only because engineers had years of cruise time remaining to develop a workaround. A failure occurring during the Jupiter encounter itself, with no time to adapt, would have been unrecoverable. Long missions demand not just patience but resilience, the ability to solve problems that no one predicted using tools that were never designed for the purpose, across distances that make every attempted fix a leap of faith lasting hours or days. The other part of the answer is more fundamental. Galileo needed to arrive at Jupiter slowly enough to be captured into orbit. A flyby spacecraft can arrive as fast as physics allows. An orbiter must match the planet's orbital environment closely enough that a manageable engine burn can slow it into a stable orbit. This means choosing a trajectory that delivers the spacecraft at lower relative velocity, which often means a longer, more circuitous path. Galileo's orbital insertion burn on December 7, 1995, lasted 49 minutes and consumed a significant fraction of the spacecraft's remaining fuel. It worked. Galileo became the first spacecraft to orbit Jupiter, beginning a mission that would last nearly 8 years and transform our understanding of the Jovian system. The contrast between flyby and orbiter timelines became even starker with subsequent missions. Juno, NASA's second Jupiter orbiter, launched on August 5, 2011 and entered Jupiter orbit on July 4, 2016. The cruise took 4 years and 11 months. Juno used an Earth gravity assist about 2 years after launch to gain the velocity needed for its transfer to Jupiter. Even with modern launch vehicles and optimized trajectories, reaching Jupiter orbit required nearly 5 years. Then compare these orbiter timelines to the fastest Jupiter flyby on record. New Horizons, launched on January 19, 2006, passed Jupiter just 13 months later, in February 2007. 13 months, barely over a year. New Horizons was the fastest spacecraft ever launched from Earth at that time, departing at roughly 36,000 miles per hour. It used Jupiter's gravity to accelerate even further, gaining about 9,000 miles per hour and redirecting its path toward Pluto. The Jupiter flyby was not the mission's goal. It was a stepping stone, a cosmic springboard. New Horizons spent only a few months in the Jovian neighborhood, collecting valuable science along the way, but it was never going to stop. It could not have stopped even if it wanted to. At the speed it was traveling, the fuel required to break into Jupiter orbit would have been many times the spacecraft's total mass. This is the central tension of outer planet exploration. Speed and stopping are fundamentally opposed. The faster a spacecraft travels, the harder it is to slow down at the destination. A flyby can be breathtakingly fast because it makes no attempt to stop. An orbiter must sacrifice speed, accept longer cruise times, and carry the fuel for a critical braking burn that determines whether the entire mission succeeds or fails. Every outer planet orbiter in history has faced this trade-off, and everyone has paid for it in years of additional travel time. Saturn provides the most dramatic illustration. Cassini-Huygens, the joint NASA-ESA mission to Saturn, launched on October 15, 1997. It entered Saturn orbit on July 1, 2004. The cruise phase lasted 6 years and 9 months, nearly 7 years of coasting through interplanetary space before the science mission even began. Cassini's trajectory was a masterpiece of gravitational choreography. After launch, the spacecraft flew inward toward the Sun, performing 2 gravity assists at Venus in April 1998 and June 1999. It then swung back past Earth in August 1999 for another gravity assist, picking up additional speed. In December 2000, Cassini flew past Jupiter, receiving yet another gravitational boost that finally placed it on its long coast towards Saturn. 4 gravity assists at 3 different planets over the course of 3 years, all to build up enough velocity to reach Saturn in a reasonable time frame, while still arriving slowly enough for orbital capture. When Cassini finally reached Saturn, it executed a 96-minute engine burn to slow itself into orbit. That single burn, carefully calculated years in advance, determined the fate of a mission that had cost over $3 billion and taken the better part of a decade to reach its destination. If the burn had failed, Cassini would have sailed past Saturn and into the outer solar system, an enormously expensive piece of space debris. The 96-minute burn deserves a closer look because it captures the terrifying arithmetic of orbital insertion at a giant planet. Cassini arrived at Saturn traveling at a velocity high enough to sail straight through the system and out the other side. The spacecraft needed to shed roughly 626 meters per second of velocity relative to Saturn to be captured into orbit. Its main engine, a 440-Newton bipropellant thruster, had been dormant for years during the cruise phase. It had to ignite perfectly after sitting idle in the cold vacuum of deep space for the better part of a decade. There was no backup. The engine either worked or it did not. Mission controllers at the Jet Propulsion Laboratory had pre-programmed the entire sequence. By the time the burn was supposed to begin, Cassini was roughly 84 light minutes from Earth. Any signal sent from mission control would take 1 hour and 24 minutes to reach the spacecraft. A round-trip communication took nearly 3 hours. Real-time intervention was impossible. If the engine failed to ignite, mission controllers would learn about it almost 3 hours after it happened, and by then Cassini would already be past Saturn and receding into the outer solar system. The engine ignited on schedule. For 96 minutes, it fired continuously, gradually slowing Cassini to a velocity where Saturn's gravity could hold it. During the burn, the spacecraft passed through the gap between Saturn's F and G rings, a region that had been carefully surveyed by earlier missions to ensure it was free of debris large enough to damage the spacecraft. A particle impact during the burn would have been catastrophic. The spacecraft passed through safely. When the burn ended, telemetry confirmed that Cassini was in orbit around Saturn. Cheers erupted at mission control. A 7-year journey, 4 gravity assists, more than 2 billion miles of travel, and the entire mission had come down to one engine performing flawlessly for 96 minutes with no possibility of human intervention. This is the cost of orbiting a distant planet. Not just years of cruise time, not just billions of dollars and decades of development, but a single moment of irreversible commitment, where the entire investment rides on one burn, one engine, one automated sequence executing correctly, 1 billion miles from the nearest repair shop. Every orbiter mission faces a version of this moment. Galileo's 49-minute Jupiter insertion burn, Juno's 35-minute capture maneuver. Each one is the culmination of years of travel and carries the same unforgiving stakes. If the burn works, the science begins. If it fails, everything is lost. There are no partial successes in orbital insertion at a giant planet. The burn succeeded. Cassini spent 13 years orbiting Saturn, studying the planet, its rings, and its moons in extraordinary detail, including deploying the Huygens probe to the surface of Titan in January 2005. The mission was one of the most scientifically productive in the history of space exploration, but it required 7 years of patience just to reach the starting line. The European Space Agency's JUICE mission, launched in April 2023, is currently on its way to Jupiter. It will not arrive until 2031. The cruise will take approximately 8 years and will include gravity assists at Earth and Venus. JUICE is designed to study Jupiter's icy moons, particularly Ganymede, Europa, and Callisto. It will eventually enter orbit around Ganymede, becoming the first spacecraft to orbit a moon other than Earth's. But the 8-year cruise means that the scientists who designed the mission's instruments and planned its observations must wait nearly a decade before receiving their first orbital data. Some of them began working on the mission in the early 2000s. By the time JUICE delivers its primary science, those researchers will have spent roughly 3 decades on a single project. NASA's Europa Clipper, launched in October 2024, is taking a different approach. Rather than entering orbit around Europa directly, which would expose the spacecraft to lethal doses of Jupiter's radiation, Europa Clipper will orbit Jupiter and make dozens of close flybys of Europa over several years. Even this indirect approach requires a cruise of roughly 5.5 years to reach Jupiter. These timelines reveal something profound about the scale of the outer solar system. Jupiter is the closest of the giant planets, and reaching its orbit still takes between 1 and 8 years depending on the mission type. Saturn is nearly twice as far, and missions require 6 to 7 years of cruise time. These are not inconveniences. They are structural features of the solar system. The distances are so vast, and the energy requirements so demanding that multi-year cruise phases are simply the cost of doing business. And the cruise phase is not idle time. Spacecraft must maintain communications with Earth across hundreds of millions of miles. Their instruments must be kept calibrated. Their trajectories must be monitored and occasionally corrected. Power systems must function flawlessly for years in the cold vacuum of deep space. A spacecraft that launches perfectly, survives every gravity assist, and coasts for half a decade without a single critical failure is a remarkable engineering achievement. The fact that missions like Galileo, Cassini, and Juno accomplish this routinely speaks to the extraordinary competence of the teams that built and operated them. But it also speaks to the unforgiving nature of the solar system. There are no service stations between Earth and Jupiter, no rescue missions, no second chances. If something breaks during a 7-year cruise, the mission is over. The gravity assist technique that makes these missions possible also imposes its own constraints. A gravity assist requires the assisting planet to be in the right position at the right time. Jupiter, which orbits the Sun once every approximately 12 years, is not always conveniently placed for a gravity assist. Mission designers must wait for favorable alignments, which may only occur every few years for a given trajectory type. If a mission misses its launch window, the next opportunity with the same planetary geometry might not arise for a decade or more. The interplay between launch windows, gravity assists, and cruise times creates a web of scheduling constraints that can delay a mission by years before it even leaves the ground. This web of constraints also means that no two missions to the same planet follow the same path. Pioneer 10 flew a direct trajectory to Jupiter. Galileo looped through the inner solar system, collecting gravity assists. Juno used an Earth flyby. New Horizons took the fastest possible path. Cassini visited Venus twice, Earth once, and Jupiter once on its way to Saturn. Each mission's trajectory was custom designed based on the planetary positions available during its launch window, the mass of the spacecraft, the power of the launch vehicle, and the specific scientific objectives. There is no standard route to Jupiter or Saturn, just as there is no standard travel time. Each mission negotiates its own deal with the gravitational architecture of the solar system. What emerges from this picture is a solar system that operates on timescales far removed from human experience. A 5-year cruise to Jupiter is longer than most doctoral programs. A 7-year cruise to Saturn spans an entire phase of a child's development from infancy to second grade. Scientists who propose these missions know they are committing to a significant fraction of their professional lives before the first data arrives. Mission controllers who monitor spacecraft during cruise phases spend years performing the same careful, meticulous checks on a machine that is doing almost nothing except falling through space along a predetermined arc. And yet, Jupiter and Saturn are the accessible outer planets. They are the ones we have visited repeatedly. They are the ones with active orbiting missions right now. They are the easy cases. Beyond Saturn, the solar system enters a realm where the word patience takes on a meaning that stretches past anything most people have ever contemplated. Uranus and Neptune are so distant, so difficult to reach, and so rarely aligned for favourable trajectories that only one spacecraft in all of human history has ever visited either world. The travel times do not double, they do not triple. They enter a domain where a single mission can span the better part of a human generation, and the challenges waiting out there are not just about distance. They're about power, communication, survival, and the institutional willpower to commit to a journey whose end no one currently working on it may live to see. In the entire history of human spaceflight, only one machine has ever seen Uranus up close. Only one has ever visited Neptune. The same machine did both. Voyager 2, a spacecraft roughly the size of a compact car, powered by a plutonium battery producing less electricity than it takes to run a microwave oven, crossed the orbits of 4 giant planets in 12 years, and returned more data about the outer solar system than every other mission combined. No spacecraft has returned to either ice giant since. That was nearly 4 decades ago, and the reasons why tell you everything about what it means to travel to the far edges of our planetary neighborhood. The story of Voyager 2 begins not with engineering or funding, but with celestial geometry. In the late 1960s, a NASA engineer named Gary Flandreau was calculating trajectories for potential missions to the outer planets when he noticed something remarkable. Jupiter, Saturn, Uranus, and Neptune were drifting into an alignment that would allow a single spacecraft to visit all 4 worlds in sequence, using gravity assists at each planet to reach the next. This alignment occurs roughly once every 175 years. The previous opportunity had come and gone in the early 1800s, decades before humans had even invented the aeroplane. The next would not arrive until the 2150s. The late 1970s represented a window that would not reopen within any living person's lifetime. Think of the alignment as a combination lock. 4 massive planets, each orbiting the Sun at a different speed, each at a different distance, must all be positioned so that a spacecraft flying past one is flung directly toward the next. Jupiter orbits the Sun once every 12 years. Saturn takes 29 years. Uranus takes 84. Neptune takes 165. Getting all 4 into the right relative positions is not just unlikely on any given year. It requires a specific geometric arrangement that takes nearly 2 centuries to repeat. The window that opened in the late 1970s was not a matter of convenience. It was a matter of cosmic scheduling. NASA originally envisioned an ambitious Grand Tour program that would send multiple pairs of advanced spacecraft to exploit this alignment. Budget pressures in the early 1970s killed the Grand Tour in its original form. What survived was a scaled-down mission called Mariner Jupiter-Saturn, which eventually became the Voyager program. 2 spacecraft would be built with a primary mission to study Jupiter and Saturn. The extended mission to Uranus and Neptune was never guaranteed. It was preserved as an option, contingent on whether Voyager 1 successfully completed its Saturn objectives and whether Voyager 2 survived long enough to continue. Voyager 2 launched on August 20th, 1977, 16 days before its twin, Voyager 1. Despite launching first, Voyager 2 travelled on a slower trajectory because its path was designed to keep the Uranus and Neptune options open. This meant accepting a longer cruise to Jupiter and a different Saturn flyby geometry than Voyager 1. The 2 spacecraft were not interchangeable. Their trajectories were tailored to different objectives. Voyager 1 was sent on a faster path that prioritized a close flyby of Saturn's moon Titan, which redirected it sharply out of the ecliptic plane and ended any possibility of continuing to Uranus. Voyager 2's path sacrificed the close Titan encounter to preserve the trajectory needed for the Grand Tour extension. Voyager 2 reached Jupiter in July 1979, roughly 2 years after launch. The encounter lasted several months as the spacecraft approached, studied, and then departed the Jovian system. Jupiter's gravity bent Voyager 2's path and accelerated it towards Saturn. The spacecraft reached Saturn in August 1981, approximately 4 years after leaving Earth. Again, months of observation surrounded the closest approach. Saturn's gravity redirected Voyager 2 toward Uranus, setting up the longest uninterrupted coast of the mission. 4.5 years of silence followed. From August 1981 to January 1986, Voyager 2 fell through interplanetary space with almost no major events. The spacecraft was functioning. Its instruments were healthy. Its plutonium power source was slowly decaying, producing less electricity each year. Mission controllers at the Jet Propulsion Laboratory monitored the spacecraft and uploaded software patches to prepare for the Uranus encounter. They reprogrammed the onboard computers to compensate for the dimmer light conditions at Uranus, where sunlight is nearly 400 times weaker than on Earth. They adjusted the camera exposure times and data compression algorithms to squeeze every possible bit of information through a communication link that grew weaker with every passing month. On January 24th, 1986, Voyager 2 made its closest approach to Uranus, passing within roughly 50,000 miles of the planet's cloud tops. The encounter was brief. The spacecraft was moving at nearly 45,000 miles per hour relative to Uranus. It had no capability to slow down or enter orbit. The entire close encounter phase, the period during which the spacecraft was near enough to collect high-resolution data, lasted only a few hours. But those hours produced the only close-up observations of Uranus humanity has ever obtained. Voyager 2 discovered 10 previously unknown moons, bringing the total known at the time to 15. It revealed that Uranus's magnetic field is dramatically tilted, offset from the planet's center, and inclined nearly 60 degrees from its rotational axis. It observed the planet's ring system in detail, confirming that the rings were dark, narrow, and composed of large particles unlike anything seen at Jupiter or Saturn. It photographed the 5 major moons, revealing Miranda's bizarre fractured surface with geological features unlike anything seen elsewhere in the solar system. All of this from a spacecraft that had already been operating for 8.5 years, far beyond its original 5-year design life, using instruments designed in the early 1970s. The discoveries at Uranus were scientifically transformative, but they also carried a deep undercurrent of frustration. Voyager 2's cameras revealed Miranda, the smallest of the 5 major moons, to be one of the strangest objects in the solar system. Its surface is a patchwork of radically different terrains. Enormous chevron-shaped features called coronae dominate parts of the landscape, bordered by ridges and grooves that suggest violent geological upheaval at some point in the moon's history. One cliff face, named Verona Rupes, was initially estimated to rise as high as 12 miles from base to crest, which would make it the tallest known cliff in the solar system, though more recent analyses suggest the true height may be considerably lower. Scientists debated whether Miranda had been shattered by a giant impact and reassembled itself gravitationally, or whether internal tidal heating had driven geological processes that reworked the surface from within. Nearly 4 decades later, the debate is not settled. It cannot be settled with the data Voyager 2 collected during a flyby lasting hours. An orbiter spending months or years studying Miranda could measure its gravitational field, map its surface composition, and determine whether geological activity continues today. Without that orbiter, Miranda remains a puzzle frozen in the handful of images Voyager 2 managed to capture before racing onward toward Neptune. The Neptune encounter produced equally tantalizing mysteries. Voyager 2 measured wind speeds in Neptune's atmosphere exceeding 1,200 miles per hour, the fastest winds recorded on any planet in the solar system. This was baffling. Neptune receives very little energy from the Sun. At its distance of roughly 2.8 billion miles, sunlight is approximately 900 times dimmer than on Earth. Something internal is driving those winds, some source of heat energy radiating from Neptune's interior that scientists still do not fully understand. Neptune emits roughly 2.6 times more energy than it receives from the Sun, indicating a powerful internal heat source. But the mechanism generating that heat and channeling it into atmospheric dynamics remains an open question that no telescope on or near Earth can resolve. Then Voyager 2 turned toward Neptune. Another 3.5 years of coasting followed. The spacecraft continued to weaken. Its power output dropped further. The communication signal grew fainter as the distance from Earth increased. By the time Voyager 2 approached Neptune, it was transmitting data at a rate slower than a 1980s dial-up modem. Mission controllers had to develop new data compression techniques and coordinate with radio telescopes around the world to capture the feeble signal. The communication challenge at Neptune's distance was unlike anything previously attempted in spaceflight. Voyager 2's radio transmitter operated at roughly 23 watts, comparable to the power of a refrigerator light bulb. By the time that signal reached Earth after traveling nearly 2.8 billion miles, it had spread out so much that the power arriving at the receiving antenna was less than 1/millionth of a billionth of a watt. Extracting meaningful data from a signal that faint required the largest radio dishes on Earth working in concert. NASA's Deep Space Network antennas in California, Spain and Australia were all enlisted, and their signals were combined with those from additional radio telescopes to create an effective collecting area large enough to catch Voyager 2's whispered transmissions. The round-trip communication delay at Neptune was over 8 hours. A command sent from Earth in the morning would not receive a response until the late afternoon. This meant that every maneuver during the Neptune encounter had to be pre-programmed days or weeks in advance. The spacecraft operated on a detailed sequence of instructions uploaded before the encounter began. If anything went wrong, if an instrument malfunctioned or a pointing error occurred, mission controllers could not intervene in real time. They would learn about the problem hours after it happened and could only upload a corrective command that would arrive hours after that. The spacecraft was effectively autonomous during the critical encounter phase, relying on software written years earlier by engineers who had to anticipate every possible contingency without the luxury of a test run. This operational reality highlights a dimension of outer solar system exploration that has no parallel in inner solar system missions. At Mars, the round-trip communication delay ranges from roughly 6 minutes at closest approach to about 44 minutes when the planets are on opposite sides of the Sun. That is long enough to prevent joystick control but short enough to respond to problems within an operational shift. At Neptune, the delay transforms mission operations into something closer to sending a letter than making a phone call. Every instruction is a commitment made hours before its consequences are known. Every observation is planned days in advance. The spacecraft must be trusted to execute flawlessly in conditions that cannot be verified until long after the moment has passed. On August 25, 1989, Voyager 2 made its closest approach to Neptune, skimming within roughly 3,000 miles of the planet's cloud tops. This was the closest flyby of the entire Grand Tour, a deliberately risky maneuver designed to maximize scientific return from what everyone knew would be humanity's only visit to Neptune for decades, possibly for the rest of the century. The gamble paid off spectacularly. Voyager 2 discovered 6 new moons, observed Neptune's faint ring system, detected auroral activity in the planet's magnetosphere, and captured stunning images of the Great Dark Spot, a massive storm system comparable in size to Earth. The spacecraft also performed a close flyby of Triton, Neptune's largest moon. Triton revealed itself as one of the most extraordinary worlds in the solar system. Its surface was geologically young, covered in nitrogen and methane ices, with active geysers erupting dark material miles into the thin atmosphere. Triton orbits Neptune in the opposite direction to the planet's rotation, a retrograde orbit that strongly suggests it was captured from the Kuiper belt rather than forming alongside Neptune. This single flyby of a single moon generated scientific questions that remain unanswered nearly 4 decades later. 12 years. That is how long Voyager 2's Grand Tour took from launch to Neptune. 12 years to fly past 4 planets, using each one's gravity to reach the next. And this was the fastest possible version of the journey, enabled by a planetary alignment that will not repeat until roughly 2153. Without the alignment, without the sequential gravity assists, reaching Neptune on a direct Hohmann transfer would have taken approximately 30 years. The Grand Tour was a masterpiece. It was also unrepeatable, and in the decades since Voyager 2 left Neptune behind, no spacecraft has returned to either ice giant. The reasons illuminate the deepest challenges of outer solar system exploration. Distance is the most obvious obstacle, but not the most important one. Uranus orbits the Sun at an average distance of roughly 1.8 billion miles. Neptune orbits at about 2.8 billion miles. These distances are so large that even light, travelling at 186,000 miles per second, takes over 2.5 hours to reach Uranus, and more than 4 hours to reach Neptune. Communication with a spacecraft at Neptune involves a round-trip signal delay of over 8 hours. A command sent from Earth in the morning would not receive a response until the evening. Real-time control is impossible. Every maneuver, every observation, every response to an unexpected problem must be planned in advance and executed autonomously by the spacecraft's onboard computers. Power is a more fundamental constraint. In the inner solar system, spacecraft rely on solar panels. Sunlight at Earth's distance provides roughly 1,360 watts per square meter. At Jupiter, that number drops to approximately 50 watts per square meter. At Saturn, it falls to roughly 15. At Uranus, it is less than 4. At Neptune, it drops to roughly 1.5. Solar panels large enough to generate meaningful electricity at Neptune would need to be the size of a football field, and even then, they would produce barely enough power to run the spacecraft's basic systems. This is why every mission to the outer solar system beyond Jupiter has relied on radioisotope thermoelectric generators, commonly called RTGs. These devices convert the heat from decaying plutonium-238 into electricity. They produce modest power, typically a few hundred watts at the start of a mission, and their output declines gradually as the plutonium decays. Voyager 2's RTGs produced about 470 watts at launch. By the time the spacecraft reached Neptune, that figure had dropped to around 400. Today, decades later, the output has fallen below 300 watts, and mission controllers have had to shut down instruments one by one to keep the most critical systems running. The problem for future missions is that plutonium-238 is extraordinarily scarce. The United States stopped producing it in the late 1980s. Russia supplied some for a period, but those arrangements ended. NASA resumed limited domestic production in 2015, but the quantities are small. Each RTG requires several kilograms of plutonium-238, and a large outer planet mission might need 3 or more RTGs. The production pipeline is measured in grams per year, not kilograms. This scarcity has become a bottleneck for outer solar system exploration. Even if the funding and the launch vehicle are available, there may not be enough plutonium to power the spacecraft. These constraints explain why the scientific community has been advocating for a dedicated ice giant mission for decades, without seeing one materialize. The most recent Planetary Science Decadal Survey, published in 2022, identified a Uranus orbiter and probe as the highest priority flagship mission for the coming decade. The original plan called for a launch in 2031 or 2032, using a Falcon Heavy rocket. That timing would have allowed a gravity assist at Jupiter, reducing the cruise time to approximately 13 years. The spacecraft would arrive at Uranus around 2044 or 2045. 13 years, just the cruise phase, and that timeline assumed the Jupiter gravity assist window would be available. Since the Decadal Survey's publication, budget constraints have pushed the likely launch date into the mid to late 2030s. Missing the Jupiter window means the spacecraft would need to take a longer, less efficient trajectory. Without the Jupiter assist, the cruise to Uranus could stretch to 15 years or more. A launch in 2038 could mean arrival at Uranus no earlier than 2053. The scientists who are designing this mission today, many of whom are currently in their 30s and 40s, would be in their 70s or 80s by the time the first orbital data arrives. Some will not live to see it. This is not speculation. It is actuarial reality. Neptune is even more daunting. The Neptune Odyssey concept, studied as a potential flagship mission alongside the Uranus orbiter, envisions a spacecraft launched in 2033 on a 16-year cruise. It would arrive at Neptune around 2049. The mission would deploy an atmospheric probe and orbit the planet for roughly 4 years, studying Neptune, its rings, and its moons, particularly Triton. The scientific case for visiting Neptune is overwhelming. Triton alone, with its active geology, its captured Kuiper Belt object origins, and its potential subsurface ocean, would justify the mission. But 16 years of cruise time, followed by 4 years of science operations, means the mission would span 2 decades from launch to completion. Including development time, the full life cycle from initial funding to final data analysis could stretch to 35 or 40 years. The James Webb Space Telescope has provided tantalizing new observations of both ice giants from afar. In 2023, Webb captured detailed infrared images of Uranus, showing its ring system, several moons, and atmospheric features with clarity never achieved from Earth or Earth orbit. Similar observations of Neptune revealed cloud patterns and atmospheric dynamics that raise as many questions as they answer. These remote observations are scientifically valuable, but they also underscore how much we are missing without an orbiter. Webb can see the planets from a distance of billions of miles. It cannot measure magnetic fields, sample atmospheres, map gravitational fields, or study moons up close. Only a dedicated spacecraft in orbit can do those things, and getting one there takes more than a decade. The Uranus system presents unique scientific puzzles that demand an orbiter. The planet is tilted on its side, with an axial tilt of approximately 98 degrees. It essentially rolls around its orbit like a ball. This extreme tilt means its seasons are unlike anything else in the solar system. Each pole spends roughly 42 years in continuous sunlight, followed by 42 years in darkness. Voyager 2 flew past during the southern hemisphere's summer solstice, when one pole was pointed almost directly at the sun. A new mission arriving before approximately 2049 would observe the planet during a different season, providing crucial comparative data. If the mission arrives too late, it will encounter nearly the same seasonal geometry Voyager 2 saw, losing a once-in-a-lifetime opportunity to study seasonal change on an ice giant. This seasonal constraint adds urgency to an already pressured timeline. The decadal survey emphasized the scientific importance of arriving at Uranus well before southern spring begins around 2049. A launch in the early 2030s would satisfy this requirement. A launch in the late 2030s might not. Every year of delay narrows the window for the best possible science. The solar system does not wait for budget negotiations or political cycles. The planets continue their orbits regardless of whether humanity is ready to visit them. Neptune's system offers different but equally compelling science. Neptune's atmosphere displays a complexity that belies its distant frozen appearance, with dynamic cloud bands, enormous storm systems that appear and vanish over decades, and a stratosphere far warmer than simple solar heating models predict. The mechanisms producing this atmospheric activity remain poorly understood. Neptune also has a complex and poorly characterized ring system, a tilted and offset magnetic field similar to, but distinct from Uranus's, and the captured moon Triton, which may harbor a subsurface liquid water ocean beneath its icy crust. Triton's geysers, observed by Voyager 2, suggest ongoing geological activity driven by tidal heating or some other internal energy source. Understanding Triton could provide insights into the habitability of icy worlds throughout the solar system and beyond, but reaching Neptune with an orbiter means accepting cruise times that challenge human institutions. 13 to 16 years is longer than most government funding cycles. It is longer than most scientists spend at a single institution. It is longer than the gap between the proposal of a mission and the typical lifespan of the political administration that approved it. Space agencies must convince governments to commit billions of dollars to a project whose primary results will not arrive until the next generation of scientists is running the laboratories. This requires a level of institutional patience that is rare in human affairs. The Voyager program succeeded partly because it was designed as a short mission that kept getting extended. Nobody had to approve a 30-year plan up front. The primary mission to Jupiter and Saturn was funded for 5 years. When it succeeded, the extension to Uranus was approved incrementally. When that succeeded, Neptune was added. Each step was a relatively small commitment building on proven success. A dedicated ice giant orbiter does not have this luxury. It must be approved, funded, built, launched, and operated as a single multi-decade commitment from the beginning. The cruise phase alone exceeds the total mission duration of most planetary spacecraft ever built. There is also the human element. The engineers who build a spacecraft launched in 2035 will be in their 60s or older by the time it reaches Uranus. The graduate students who help design the instruments may be department chairs by the time the first data arrives. Mission operations teams must be trained and maintained for more than a decade of cruise phase monitoring before the intense science phase even begins. Knowledge must be transferred across generations of engineers and scientists. Documentation must be maintained. Software must be updated. Institutional memory must be preserved. All of this costs money, attention, and organizational discipline over timescales that test the limits of human project management. And yet, the scientific community continues to advocate for these missions precisely because nothing else can answer the questions they pose. Remote observations from Earth-based telescopes and space telescopes like Webb provide context and motivation, but they cannot replace the measurements that only a spacecraft in orbit can make. The internal structure of Uranus and Neptune, the composition and dynamics of their atmospheres, the geology and potential habitability of their moons, the behavior of their magnetic fields, these questions require proximity. They require instruments flying through the environment, sampling the particles, measuring the fields, photographing the surfaces from close range. The ice giants also represent the most common type of planet in the galaxy. Exoplanet surveys have revealed that planets roughly the size of Uranus and Neptune are far more numerous than gas giants like Jupiter and Saturn, or rocky worlds like Earth. Understanding our own ice giants is essential for interpreting observations of these distant worlds. Every exoplanet scientist working on sub-Neptune-sized worlds is limited by the fact that humanity has only one brief flyby's worth of data on this entire class of planet. A dedicated orbiter mission would not just advance solar system science, it would provide a ground truth reference point for understanding thousands of worlds orbiting other stars. The distances to the ice giants are not just numbers, they are barriers that test every aspect of human capability. Technology, funding, patience, institutional commitment, even the biological lifespan of the scientists involved. Reaching Uranus or Neptune is not merely difficult, it is a generational project, a relay race where the runners who start the race will hand the baton to successors they may never meet. Voyager 2 proved it is possible. A small spacecraft with 1970s technology crossed the entire outer solar system in 12 years. But Voyager 2 only flew past. It never stopped. It never orbited. It collected hours of close-up data at each planet and then moved on, forever. Now comes the question that everything so far has been building toward. If humanity wanted to actually visit every planet, not just fly past but orbit, study, perhaps even land, what would the total journey look like? How many years? How many spacecraft? How many separate missions? And what does the answer reveal about the true nature of the solar system we call home? Now the question can finally be answered. How long does a mission to every planet actually take? The answer depends entirely on what you mean by every planet, what you mean by mission, and whether you are willing to accept a truth that most people find deeply unsettling. Because the honest answer is not a single number, it is a spectrum of numbers spanning from roughly a dozen years to several human lifetimes, depending on choices that fundamentally reshape what the journey means. Start with the simplest version, a flyby of every planet. Not stopping, not orbiting, not landing. Just passing close enough to photograph each world and collect basic measurements before moving on. This is what Voyager 2 came closest to achieving, and its grand tour remains the only template humanity has for visiting multiple outer planets in a single mission. Voyager 2 flew past Jupiter, Saturn, Uranus, and Neptune in 12 years. That covered 4 of the 7 other planets in the solar system, but it skipped 3. It never visited Mercury, Venus, or Mars. And the reason it skipped them reveals a fundamental problem with the entire concept of an all-planet mission. Visiting the inner planets and the outer planets requires opposite strategies. To reach the outer planets, a spacecraft must gain energy. It must climb outward from the Sun, moving to higher and slower orbits. Gravity assists at Jupiter and Saturn provide the boosts needed to reach Uranus and Neptune. The entire trajectory is designed to push the spacecraft farther from the Sun with each encounter. To reach Mercury, as explained earlier, a spacecraft must lose energy. It must fall inward toward the Sun, shedding the enormous orbital velocity that Earth provides at launch. These two objectives are not just different, they are contradictory. No single trajectory can efficiently do both. A spacecraft cannot simultaneously gain energy to reach Neptune and lose energy to reach Mercury. The physics does not allow it. This means an all-planet flyby cannot be a single mission with a single spacecraft on a single trajectory. At minimum, it would require 2 separate spacecraft launched on 2 separate trajectories. One would handle the inner solar system, visiting Venus, Mars, and Mercury through a series of gravity assists and braking maneuvers. The other would handle the outer solar system, using Jupiter as a springboard to reach Saturn, Uranus, and Neptune in sequence. For the inner spacecraft, the timeline is surprisingly long. Venus can be reached in roughly 5 months. Mars can be reached in roughly 7 months. But Mercury, even on a flyby trajectory, requires careful maneuvering near the Sun. Mariner 10 reached Mercury in about 5 months using a Venus gravity assist. A mission that combined flybys of Venus, Mars, and Mercury in sequence would need to navigate complex multi-planet trajectories that might take 3 to 5 years depending on launch windows and planetary positions. The inner solar system is compact in distance but complicated in orbital mechanics. For the outer spacecraft, Voyager 2 provides the benchmark, 12 years from launch to Neptune, with gravity assists at each planet along the way. But Voyager 2 benefited from the once every 175-year alignment. Without that alignment, visiting all 4 outer planets in sequence is not feasible with gravity assists. A mission launched today would need to find a different set of planetary positions and design a trajectory that might be less efficient, potentially stretching the timeline to 15 or even 20 years for a Jupiter to Neptune tour. So the absolute minimum for a flyby of every planet, under the most optimistic assumptions, is roughly 12 to 15 years using 2 spacecraft. That is the cheapest, fastest, most stripped-down version of the answer. 2 machines, launched within a few years of each other, each flying past its assigned planets and sending back data during brief encounters. The total data return would be modest. Flybys produce hours or days of close-up observations at each planet. The spacecraft would collect postcards, not encyclopedias, but every planet would be visited within a single human generation. Now, consider what happens when the goal shifts from flying past to staying. An orbiter mission represents a fundamentally different commitment. Entering orbit around a planet requires carrying enough fuel to perform a braking burn upon arrival. This adds mass, which demands a larger rocket, which limits trajectory options, which often extends cruise times. Every orbiter mission in history has taken significantly longer to reach its target than a comparable flyby. Using historical mission durations as a rough guide, the timeline for orbiting each planet individually looks something like this. Venus orbit insertion can be achieved in under a year. Magellan reached Venus orbit in roughly 15 months after launch. Mars orbit insertion typically takes 7 to 10 months. Mars Odyssey arrived in about 200 days. Mercury orbit insertion, as BepiColombo is demonstrating, requires approximately 7 to 8 years of gravity assist maneuvering. Jupiter orbit insertion takes 5 to 6 years, as shown by Juno. Saturn orbit insertion takes roughly 7 years, as Cassini demonstrated. Uranus orbit insertion, based on current mission concepts, would require 13 to 15 years with a Jupiter gravity assist, or longer without one. Neptune orbit insertion is estimated at 12 to 16 years, depending on the trajectory. But these timelines cannot simply be added together. Each mission requires its own spacecraft, its own launch vehicle, its own launch window, and its own trajectory. You cannot launch a single spacecraft to orbit Venus, then leave Venus orbit and fly to Mars, then leave Mars orbit and proceed to Jupiter. The delta-v requirements for departing one planet's orbit and entering another's are prohibitive with current propulsion technology. Each planetary orbit is a gravitational commitment. Once a spacecraft is captured, escaping requires almost as much energy as arriving did. No existing or near-term spacecraft can carry enough fuel for multiple orbit insertions at different planets. This means that orbiting every planet requires at minimum 7 separate missions, 1 for each world. 7 spacecraft, 7 launch vehicles, 7 development programs, 7 operations teams. If each mission launched at the earliest available window and the programs ran in parallel, the overall timeline would be dominated by the longest single mission. That would be the Neptune orbiter, with a cruise time of 12 to 16 years. Adding development time, launch preparation, and the science phase at Neptune, the total program would span roughly 25 to 30 years, from initial funding to final data collection. But parallel development of 7 flagship-class missions is not realistic. No space agency on Earth has the budget, workforce, or institutional capacity to develop 7 major planetary missions simultaneously. In practice, missions are developed sequentially or in small overlapping groups. NASA currently operates or is developing missions to Mars, Jupiter, and Saturn's moon system. Adding a dedicated Mercury orbiter, a Venus orbiter, a Uranus orbiter, and a Neptune orbiter to that portfolio would require decades of sequential development even under the most generous funding assumptions. A more realistic timeline for orbiting every planet, accounting for sequential development and budget constraints, stretches to 50 or 60 years. That is not a mission. That is a multi-generational program of exploration, spanning the entire professional lives of multiple cohorts of scientists and engineers. The person who proposes the first mission in the sequence might not be alive when the last spacecraft enters orbit around its target. Now consider the most ambitious version of the question, not just orbiting, but landing on every planet. Landing adds another layer of complexity and time. For rocky planets with solid surfaces, landing is conceptually straightforward if technically demanding. Spacecraft have landed on Venus, Mars, and even Titan, Saturn's largest moon. Mercury has never been landed on, and the extreme temperature variations and lack of atmosphere make it exceptionally challenging. Landing on the gas and ice giants is a different matter entirely. Jupiter, Saturn, Uranus, and Neptune do not have solid surfaces. A spacecraft entering their atmospheres would descend through increasingly dense layers of gas until pressure and temperature crushed it. The Galileo atmospheric probe survived for roughly 58 minutes after entering Jupiter's atmosphere before being destroyed. A similar probe could be deployed at any giant planet, but it would not land in any traditional sense. It would transmit data during a brief descent before succumbing to the environment. If we define landing broadly, meaning surface landing on rocky worlds and atmospheric probe entry on giant worlds, then visiting every planet with a lander or probe adds development time and mission complexity, but does not fundamentally change the overall timeline. The cruise phases remain the dominant factor. Getting to Neptune still takes 12 to 16 years, regardless of whether the spacecraft carries a lander, an atmospheric probe, or only orbital instruments. The human dimension makes everything harder. Every timeline discussed so far involves robotic spacecraft, uncrewed machines that can coast through space for years without food, water, oxygen, or psychological support. They do not get bored. They do not get sick. They do not miss their families. A robotic spacecraft can endure a 13-year cruise to Uranus because it has no concept of time. It simply exists, drawing power from its RTG, waiting for instructions, executing commands with the same precision on day 1 as on day 4,700. Humans cannot do this. The longest continuous human spaceflight in history lasted approximately 437 days, set by Valery Polyakov aboard the Russian space station Mir in 1994 and 95. Current proposals for crewed Mars missions envision round-trip durations of roughly 2.5 years, including about 7 months of travel each way and approximately 500 days on the Martian surface waiting for the return launch window. This 2.5-year timeline is already at the edge of what medical science considers manageable for human physiology. Bone density loss, muscle atrophy, radiation exposure, cardiovascular deconditioning, and psychological stress all accumulate over extended spaceflight. A crewed mission to Jupiter, lasting 5 to 6 years minimum, would push far beyond any experience base humanity possesses. A crewed mission to Neptune, requiring 12 to 16 years of travel, is not currently within the realm of feasible engineering. It would require breakthroughs in life support, radiation shielding, artificial gravity, psychological resilience, and onboard medical capability that do not yet exist. Even the crewed Mars mission, the most modest possible version of human interplanetary travel, reveals how completely orbital mechanics dictates the terms. The popular image of a Mars mission involves astronauts flying to Mars, spending a few weeks exploring and flying home. The reality imposed by the solar system is nothing like that. A crewed Mars mission using a standard home and transfer would begin with a launch during a favorable window, followed by a cruise of roughly 7 to 9 months. The crew would arrive at Mars, enter orbit, or land on the surface, and begin their work. But they cannot come home whenever they choose. A return home and transfer requires Earth and Mars to be in the correct relative positions, and that alignment does not occur until roughly 500 days after the crew arrives. 500 days, nearly a year and a half. The astronauts must remain on Mars for that entire period regardless of whether their mission objectives are complete, regardless of medical emergencies, regardless of equipment failures, regardless of psychological breakdown. The planets are not aligned for a return trip. The launch window is closed. The solar system does not offer early departures. This forced surface stay is not a design choice. It is not a scheduling preference. It is an orbital constraint as rigid as any law of physics. The total mission duration, accounting for outbound cruise, surface stay, and return cruise, comes to approximately 2.5 years, roughly 9 months out, roughly 500 days on Mars, roughly 9 months back. Some proposed mission architectures use faster transfer trajectories that reduce cruise time but increase fuel requirements and radiation exposure. Others propose opposition-class missions with shorter surface stays but longer total flight times and a Venus flyby on the return leg that adds complexity and risk. Every variant is a different negotiation with the same underlying orbital mechanics. None of them escape the fundamental constraint that Earth and Mars orbit the Sun at different rates, and you cannot go home until the geometry allows it. This means that the simplest possible crewed interplanetary mission A round trip to the single most accessible planet beyond Earth lasts 2.5 years at minimum. The crew must be entirely self-sufficient for that duration. Every calorie of food, every litre of water, every breath of oxygen, every medical supply, every spare part must either be carried from Earth or produced on Mars. Communication with Earth involves delays of 3 to 22 minutes each way depending on orbital positions. Real-time conversation is impossible. If a crew member suffers a serious medical emergency, the nearest hospital is hundreds of millions of miles away and months of travel time distant. The crew is alone in a way that no human being has ever experienced, isolated not by choice or by geography, but by the geometry of two planets orbiting the Sun at different speeds. This is what the solar system demands for a visit to just one planet, one nearby, relatively accessible, well-studied rocky world. And the dominant factor in the mission timeline is not engine power or spacecraft capability. It is the 500 days of forced waiting, while two planets slowly drift into the positions that orbital mechanics requires for a return flight. Even at the human scale, the solar system imposes its schedule with absolute authority. A crewed mission to every planet is therefore not a meaningful concept with present or near-future technology. The inner planets might be accessible to crewed missions within the coming century. Mars almost certainly will be. Venus flyby missions have been studied. Mercury crewed missions are theoretically possible, but offer little advantage over robotic exploration given the extreme environment. The outer planets, however, remain the exclusive domain of robots for the foreseeable future. The distances are simply too vast, the travel times too long, and the human body too fragile for journeys measured in decades. So, what is the grand total? The answer fractures into layers depending on ambition. A flyby of every planet using 2 robotic spacecraft launched on optimized trajectories could be accomplished in roughly 12 to 20 years. This is the fastest version, the leanest possible answer to the title question. It assumes favorable launch windows, proven gravity assist techniques, and minimal spacecraft complexity. The scientific return would be significant but shallow. Brief encounters at each world, measured in hours or days rather than months or years. An orbital mission to every planet using 7 separate robotic spacecraft developed and launched over several decades could span 30 to 60 years from first launch to final data return. This version provides deep, sustained study of each world, but requires institutional commitment across multiple human generations. It demands consistent funding, technology transfer between generations of engineers, and a level of political patience that is rare in democratic societies. A comprehensive exploration program that includes orbiters, landers, atmospheric probes, and sample return missions at every planet could stretch to a century or more. This is the version that fully answers every scientific question humanity currently has about its planetary neighbours. It is also the version that no one alive today will see completed. And here is where the true lesson of this journey reveals itself. The question that opened this episode sounded simple. How long does a mission to every planet take? It sounded like a question with a number for an answer. 7 years, 15 years, 40 years. But the real answer is not a number. It is a realization. The solar system is not a collection of destinations waiting to be checked off a list. It is a moving machine, a vast gravitational architecture in which every world orbits at its own speed, follows its own path, and occupies a position that changes every single day. There is no fixed route from Mercury to Neptune. There is no itinerary. There is no schedule that the planets will cooperate with. Every mission to every planet must be individually negotiated with the geometry of the solar system at the specific moment of launch. A spacecraft cannot simply point at a planet and go. It must enter an orbit around the Sun that intersects the target planet's orbit at precisely the right time and place. It must carry enough energy to match velocities with its destination, or accept a fleeting flyby and move on. It must time its launch within a window that may open for only a few weeks and then close for years. And if the goal is to visit multiple planets, the constraints multiply. Each additional destination demands its own trajectory adjustment, its own gravity assist, its own launch window. Number 1. The planets do not line up on command. They follow their orbits with absolute indifference to human ambition. This is why Voyager 2's grand tour was a once-in-a-lifetime achievement in the most literal sense. The planetary alignment that made it possible will not recur for roughly 175 years. The next time all 4 outer planets are positioned for sequential gravity assists, everyone alive today will be long gone. The mission was not just a triumph of engineering, it was a triumph of timing. Humanity happened to develop spaceflight capability at precisely the moment when the solar system's geometry made the grand tour possible, a generation earlier or later, and it could not have been done. The same principle applies to every future mission. A Uranus orbiter launched in 2032 could use a Jupiter gravity assist and arrive in 13 years. The same mission launched in 2038, after Jupiter has moved out of position, and might take 15 years or more. The planets do not wait. They do not slow down. They do not rearrange themselves for human convenience. Every year of delay on Earth translates to years of additional travel time in space, or worse, the complete closure of a trajectory option that will not reopen for decades. This is what makes the solar system so profoundly different from any travel experience humans have on Earth. On Earth, the destination sits still. The road does not move. The airport does not orbit. The distance between 2 cities does not change from one year to the next. In the solar system, everything moves. Every destination is a moving target. Every route is a curve. Every schedule is dictated by the geometry of orbits that no human can control. A mission to every planet is not a road trip. It is not a checklist. It is not a vacation itinerary. It is a decades-long negotiation with the moving architecture of gravity itself. The planets orbit the Sun at speeds ranging from over 100,000 miles per hour for Mercury to roughly 12,000 miles per hour for Neptune. They are all falling around the Sun in their own ellipses, following paths laid down by the laws of physics 4.5 billion years ago when the solar system formed. A spacecraft entering this system is a tiny intruder, borrowing momentum, stealing energy, threading through gravitational fields with precision measured in fractions of a mile per second. The shocking truth is not that the planets are far away. Distance is just a number. The shocking truth is that even inside our own solar system, surrounded by worlds we can see with the naked eye, travel is governed by rules that make it fundamentally unlike any journey humanity has ever taken on Earth. Closer planets can take longer to reach than distant ones. Faster spacecraft can take longer to arrive if they need to stop. Launch windows open and close on schedules set by orbital mechanics, not by human readiness. And the difference between flying past a world and truly studying it can be the difference between a few months and a few decades. We live inside a gravitational machine of staggering complexity. 8 planets, dozens of major moons, and billions of smaller objects all orbiting the Sun in an intricate pattern that shifts constantly, but repeats only on timescales measured in centuries. Every mission humanity has ever launched into this machine has been a negotiation, a careful, patient, mathematically precise negotiation between what we want to learn and what the solar system's geometry will allow. A mission to every planet is possible. Humanity has the technology, we have the knowledge, we have the ambition. What we must accept is that the solar system demands something in return. It demands time, not months, not years, decades. A generation of patience to visit every world that orbits our star. And even then, the visit is not a conquest. It is a brief audience with a system that was here billions of years before us and will continue its silent clockwork billions of years after we are gone. The planets are not waiting for us. They never were. They are moving, always moving. And reaching them means learning to move with them, on their terms, at their pace, along the curving paths that gravity carved long before any human looked up at the night sky and wondered what was out there.